Is it okay?
Oh,
It started from your side?
no,
Okay.
now it is started, sir. Yes.
Okay. So I think last class I have finished up to this. Okay. So if you notice it clearly, am I audible to clearly to all of you?
Yes, sir.
Yes, sir.
Okay. If
Yes,
any
sir. Yes, sir.
difficulty, you can raise your voice so that I can increase my voice. See, first of all, this chapter, digital logic design, we have studied so far. You will notice that after digital logic design, then you are going for control unit part. Then after that machine, that is what is called machine, we can generally design with the FSM, some sign machine. Then you will get system software after the assembly. Now we no more days this part is not visible to us. High level language user. Actually, you are starting from this top level, and gradually this happen. So for any executable or apps, what are doing? This is the executable program. For making some apps, you are actually in C, Java, Fortran, like in these languages to make a your hard apps. And this part actually I am not discussing. This is the part of the assembler, very not new to us. But whatever you are doing, everything in some operating system or some library is required. After that, you will get the ISA. That is a very important point. ISA, instruction set architecture. So this is a very important part for our computer organization class. Then you will find that based on the ISA, different machine will come. And last class I have discussed, one is that IBM 370 model, another is the Intel, Intel Intel X80, 8086, 8085. These are the different Intel 80 series model already we have studied. After that, you will find some control logic that I have put a microcontrol or is a hardware. Here I have written that is particularly microprogram or hardware. We will study this also in control unit design. And finally, you will get circuits and gates, which is our motherboard. Okay, so at the organization level part, you will start from the top and gradually you will reach at this position. So this is the hierarchy also option. Okay, now after that you will find first of the concept, what is the stored program concept. I told that von Neumann already uttered this point. That means stored program concept, data or instruction, whatever maybe instruction, data or instruction, whatever you would like to access, money data or instruction, because instruction operand or data. So you have to first store in some memory. Since this is the concept of the storing process, so you have to store in the memory. So I am writing in main memory maybe. So that's why it is called stored program concept. So before execution, when data is required or for any instruction required, anything, because any program or any application is nothing but a collections of instruction will be executed on some operand or maybe is executed by operating some hardware so resources. So in these cases, so all these things should be stored flash on the memory. So that was the first our observation. Second is that this is the von Neumann already I have mentioned. Now what is the stored program concept or stored program architecture? You will find that there is a very important part, that is the memory. Everything you have to store. This architecture is very important, basic fundamentals. Maybe in earlier classes, maybe class 12, 11, you have get the idea of the von Neumann architecture, but from today's classes, you should know von Neumann. Maybe in your entire life, when you'll be research or something, they can ask you, do you know von Neumann architecture? Yes, sir. Then what is von Neumann? Sir, is the stored program concept. Then, since it is stored program concept, so there must be a presence of the memory, very important part. Now some input output is there, that is for input output organization, and finally there is a CPU. So these are the basic components. So if I write here, one is CPU, one is memory, another is the IO. Apart from these three part, you will get another very important task, very important part, that is we can say our bus, or you can say the interconnection. Okay, so this is a very important task. Now you will find that store data and program together. This is the memory part. Memory, store data and program. Our program here nothing but we call say instruction. Okay, so we will call it is a instruction. Is it clear? So in stored program, program means instruction, and here we'll find that to execute a program you need a control memory, control unit, and control unit nothing but you will find there is a ALU. Here I have written control unit. So you will find there is a ALU and there is the control unit. So ALU do the all the arithmetic and logical calculations required for the CPU processing, and control unit actually controls the entire sequence of operation. It's control the entire sequence of operation. So that is the task of the control unit. It controls the sequence of operation. Now you will find that very interesting part, the memory. It is directly connected to the CPU as well as sometimes it is connected to the IO. For abstract level it is clear, for abstract level, but you remember that CPU can't access all the memory. CPU can't access all the memory. CPU only access the main memory. I will discuss this part. So it can't access all memory. So now since this part is clear to you, you remember this point, that memory which is accessible by from our side. What happened? Suddenly it's closed. Just 1 minute. So this is the one part I am dealing with, this one, and rest of the part is that you will find here the control unit and the ALU. This our is CPU. So we will call our CPU is nothing but, sorry, our CPU is nothing but you will get that CPU is nothing but ALU plus our control unit. So whenever I will call CPU, you will consider that it is nothing but ALU plus control unit. That is the program our CPU. So that is the CPU part. It is nothing but ALU plus CU. Now memory part, I will disclose the details of the memory here. So in von Neumann architecture, these are the four components: number 1, number 2, number 3, and this bus is the number 4. These are the basic 4-unit module for stored program concept is required. After that, you will find that main for computer consists of 4 main subsystems. Already I mentioned. First one is memory, that is the main memory, or secondary also I'll consider later. Then processors, IO system, and sister I connect here. I mentioned is a bus. Now program is nothing but data and instruction. It is clear from this discussion. It's stored in main memory during execution. Remember this point, what I mentioned, during execution, because all the program may not be required entirely to be loaded in the program, that means in memory, which is not essential. Only those part of the program or instruction to be loaded in the memory for which required, or maybe which during the execution is running execution load. Because in OS you will find that process have 5 state. You will get some state is ready. After that ready, you will go to the execution, and sometime it may be wait, you have to come, and from wait queue again to ready queue, and after that it will be completed. Why happened that in execution state, any process when in execution mode, remember this point, when any process in execution mode is called program. Am I correct this definition? What is program? Any process in execution mode only we call as a program. So whatever I have written, data and instruction, sometimes we can write as a program. So this is the program. Since program, so we can know process in execution. So remember this point, process in execution is the our part for program. So program instruction are executed sequentially. This is another point, sequentially. In von Neumann, this is the fundamental bottleneck that, remember, this is the fundamental bottleneck. Can you say why it is a fundamental bottleneck? Anyone from your side? Is it possible from us to understand why it is called fundamental bottleneck? This is a challenging task.
Sir, for example, in object-oriented programming, sir,
Speak
it's more
loudly, not audible
modular
to
than
me.
sequential. Sir, am I audible now?
Yes.
Sir, for example, in object-oriented programming, we learned that rather than sequential, it's modular. Like the entire thing goes according to how, not the flow, but rather the functions that are written in the.
Simple stated parallel processing will be a difficulty problem here. Am I correct or wrong?
Yes, sir. Yes, sir.
Just is a simple word because multiple programs are there. Sorry, multiple instructions are there. It may happen that you have a 5 instruction A, B, C. It may happen that C is not depend on A and B. Not that does not depend on A and B. So when A is executed, maybe maybe A and A, A, add A, B, C. B and C will be added and then we show the A. That's the instruction I am writing. Okay. And
Your
this is
voice
the
is
instruction
breaking,
I2.
sir.
Yes. Any questions? Okay. Now I2 is there. Maybe add or add. It is using AC. C plus A plus C will be stored to A. But that time, this instruction require A, which is performed by the instruction 1. Then instruction 3 is nothing but store D or fetch D, which does not depend on instruction 1 and instruction 2.
Sir, your
That's
voice is
why
cracking, sir. Sir, your voice is cracking, sir. We could not hear anything what you said after the bottleneck portion, sir.
now I'm telling you that it happened that I1 and I2 may be dependent, but I3 instruction not dependent on I1 I2, but I can't execute I3 parallel because it is sequential. Though I am giving the expression is the pipelining, in the pipelining we will try to parallel pipelining in our latest computer, whatever you are using, desktop or laptop, all are stored program concept, von Neumann architecture. In pipelining, we will try to parallelize multiple instruction, that means simultaneously, but again the problem still there sequentially. That means if their hardware resources are independent, we would like to segment the instruction in such a way that multiple instruction can be fed in a processors to execute. But remember one point, still there is a sequential execution will be there. That means when you are executing instruction 1, there will be no chance that your execution 2 or execution 3 will be parallel. Am I getting this point or not? Maybe when you are executing 1, you are loading execution 2. Am I clear or not? When you are doing instruction 1 is loading, my point to be noted there, instruction 1 in execution mode. That time you can load instruction parallel, so your time will be saved. But I am telling that when I1 in execution, I2 in execution, never possible. It is the bottleneck of the von Neumann architecture. But still we are happy because with lot of hardware resources and pipelining, we are getting our expected speed still now. It may happen that in supercomputing architecture or maybe non-von Neumann. In non-von Neumann concept, there is no stored program. It is a non-storage concept. That's why non-von Neumann, no storage. No storage concept. Storage are there, but every time to store get the data you have to fetch from the memory, and after executing again you have to store to the memory. This concept is not there in non-von Neumann computing, but it is not in our syllabus at this moment. Our syllabus completely relies on whatever modern computer or digital computer using, which is fully von Neumann architecture. Am I clear this point? So this should be clearly, no two instructions should be done sequential or parallel. That's why, so 4 subsystem we found that in computer, that is the first memory, second CPU, third this, and these are the 4 basic unit we have studied. Now, why is memory so much important? It is found that it is a completely technology problem. That means the way CPU are developed, that means number of transistor embedded, or you can say integrated, better time is integrated in a particular CPU chip day by day increase so much. The speed of the CPU increase like in this way, the technology of the CPU. But apart from the technology of the RAM is not increased so much. So there is a huge gap in speed. Are you getting my point? Remember, this still exists. So processor performance increased at a much faster rate than memory performance, making main memory the bottleneck. So what happened there? I have to minimize this gap. At least I can come to this level, or I can go up to this level. That's why the main concept of the main memory is not sufficient to minimize the gap. So what should I do? In 1980, there is no cache. There is no cache. But in 2001, two-level cache and 90% of transistor and microprocessor increase. So this is the coming. So these are the situations are coming nowadays. So what happened there? To minimize that CPU and DRAM gap, here I mentioned DRAM, no issue, mostly DRAM are used. That's why you are going DDRM, you are getting. So most of the DRAM, so maybe your RAM is 4G, fourth generation DDR. Now it is going DDR RAM, double data rate, double data DRAM. You are consuming. That means in a RAM, particularly you are storing this time, or you can storing this time. That means in earlier only one clock pulse. If it is this is the clock signal. I think you on digital logic you have seen the clock signal. This is positive. This is negative. This is positive. This is negative. So what happened? Only positive clock pulse flip-flops are working. In negative, it is not enabled. Nowadays, both in a chip, they are doing the architecture in such a way that both negative and positives they are using. Both negative and positive clock pulse are there. Negative S trigger and positive S trigger are using to increase the double data. That's why it is concept is coming DDR RAM. Is it clear? So this concept is now happening here. Now you will find there is a memory subsystem. So this pyramid is very important. Initially, we consider the high speed memory. If we consider in the CPU, context of CPU, that is the CPU register. Very high speed memory, this part. High speed memory, that is CPU registers. Am I clear this point? High speed memory, CPU register. After that, this part completely we can as a cache memory. Speed is less than CPU register, but more than the main memory. And we call this area for our main memory. And after that main memory, the rest part we call the secondary memory, SM. And after that SM, you remember all these are different input resources are coming. Maybe your pen drive, flash drive, scanner, all these are remoted from memory, data is coming. Now, if you notice it clearly, I told in last class there, CPU is never connected with the SM. CPU is connected with the this part. So since it is not connected, so you will find there this part there is a cache memory, and cache memory is connected to the main memory also, and main memory is connected to the rest of the memory. Is it clear? So you will find that CPU is accessing cache and main memory. And I told that the data present in the main memory is also present in the cache memory, but cache is utilized here. So I already mentioned to minimize this band gap. How we can, cache is faster than main memory, so automatically it will come. So we can minimize this gap to up to this level. Am I clear? After that, you will find that I told main memory whose speed is more than secondary but slower than the cache. That's why you will find that the direct access to the CPU up to main memory. This is up to main memory. Clearly understood. Direct access to CPU up to main memory. Okay, that is what is called we call a physical RAM or our virtual memory, whatever may be. That is direct access. But indirect access to CPU, the rest of the part is indirect access. That means your hard disks or SSD, whatever may be, they have always indirect access. Nowadays, multi-level cache are introduced. Sometimes it is found that L1 cache also embedded with the CPU itself along with the CPU. That is the technology dependent and the architecture, whatever they are following organization. So nowadays it happened that L1 is inside the CPU itself. That means nowadays CPU is coming different core. Different core is there. Interconnected core are joining there to multiple processing. Inside CPU register banks is there. I will discuss register very soon. After that also some cache memory is there in a single chip. So your processor, what is called CPU, is now coming like in this way. The different variation there. Now L1 cache may be inside the CPU and rest of the part is outside the CPU. So that's why I'm giving the technology also. It is found that our core in general it is coming the still now it is the figure in KB, 5 KB, 10 KB, 16 KB, 13 KB it is coming, but L1, L2, 3 cache is coming in MB. Okay, and you will find the main memory mostly DRAM it is coming in GB. Now you are using 8 GB, still now economical for all of us. And then after that local storage or flash or hard disk it is coming in TB, and sometimes cloud storage is petabyte is coming. So like in this architecture, you know the speed is like increasing like in this way. That means when you go this way, the speed is decreasing. And when you go this way, capacity is increasing, but speed increasing. Also notice that some memories are volatile. Which memories are volatile? You will find that most of the memory are volatile up to primary memory, but rest of the memories are non-volatile. So that is the up to part of memory. Now in the register part, already I mentioned register is very fast memory and very close to the CPU. The types of memory located inside the CPU chip. So inside CPU means if I consider this is the entire CPU, so registers are present inside the CPU. Can hold a single piece of data. That means each piece of registers contain single piece of data. Very important information, useful in both data processing and control function. It is very useful data application for our control as well as the data processing application. Remember that CPU register only gets the data from cache or main memory during the subtraction, addition, whatever ALU, because inside the CPU there is a part is the ALU, and ALU is directly connected to the registers bank. And from register, data is coming from cache or main memory or from your system connected bus through secondary memory also. Register will be loaded. But CPU directly try to access the register during the execution mostly. So you will find two types of register. First of all, the programmable register that is called scratch pad. Whatever you are doing in register application, sometimes in C programming, you will find some variable declared as a register. So you can directly access the registers also instead of storing the memory in the main memory. Whatever programming you are doing, C program or something, everything instructions are loaded from the main memory, and during the CPU access each of the memory through his register bank. And these are the special register. Sometimes in technologically abstract level we call it the ABC, sometimes R1, R2. That means some instruction if I write add A, B, C, it means B and C. This will be added and will be stored to A. If I write add A, B, it means that A plus B will be loaded to A. Like in this. Anyhow, register application will be there. C, composition, then again store. And in case of add AB, the actual first instruction you have to load the value A, you have to load the value B, then do perform the addition. That means you are taking from the main memory, then taking the composition again stored in the register itself. So like in this storing process is still there. And these are the special register, that is program counter. It always points to the next instruction to be executed. Always points next instruction to be executed. Remember the purpose. Next instruction, that means when you are executing instruction 1, suppose, then what will be instruction next? Maybe I2 or maybe I5, because some loop construction there. If within the I1 there is a if condition, if it is true then I2, if it is false then I2. So maybe based on the instruction I1 you can jump to I5 also. Is it clear? So it is found that I1 instruction, which after jump you maybe go for the middle of the instruction I5, I6, I7, or maybe after I1 you go I2. Whatever may be, that where CPU will point or go for the next instruction, that content will be loaded in the PC. So PC always contains some address value, maybe 500. So you go to the instruction number 5. After that maybe 600, you are executing instruction, then each point the next instruction, you go to the next instruction, because every time it will be executed each instruction sequentially. So our PC always points to the next instruction to be executed. Clear? No PC cannot be that means used as a general purpose register. Be careful, this is the special purpose register, only for special purpose. Instruction register, where instruction will be loaded for decoding. So instruction register is a special purpose, and accumulator or working register I will mention as A and W during any pseudocode writing. If I mention A or W, you can understand that I am using accumulator. This is a special purpose register used as a temporary storage. When during ALU computations takes place, it initially stores the value in the accumulator. If you use it, then it will be again will come back, return to the our you can say value of the program. Okay, and another part is that sometimes you have to load. So it looks like in this way. Just 1 minute, I am opening another whiteboard. It's possible here. Is visible to you?
Sir, not yet. It's loading, sir.
Okay.
Yes, sir. Yes.
Sir, are you writing something right now?
Just 1 minute. I think whiteboard not visible to you?
Yes, it is visible.
Yes, sir. It
Sir,
is.
it's visible.
Yes, sir. We can see.
From my
Visible.
end, not visible. I have to cross check whether it is visible to me or not. Anyhow, I have to customize it later. For time being, it is not visible to me. So I am changing it. I will come back again later in the whiteboard later. Okay. This class I'll customize and configure it. Now my point is my slide is visible to you.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So slide is visible. I can go for this point. Actually, I would like to show that ALU is just like this type of structure. Particularly ALU, I am showing. ALU is just I am telling this is the ALU architecture. It's disturbing a lot. So ALU is just like in this way. If I say it is ALU, there is a accumulator ACC. Okay. So accumulator is directly come in this way, and one data is coming registers. There is a multiplexer either from accumulator, either from outsourcing. So this mux will do the task. Sometimes the accumulator will be loaded in the memory, or sometimes data will come from another register. So that's why it is a temporary storage. If it is found that accumulator will be repeated just I equal to suppose I plus 1. So every time I will be incremented in the storage. So this type of concept can be implemented by this way. So this is the presence of the accumulator. Okay, gradually we'll discuss this one. Now we come to the point that is the register. Remember, two type registers there. One is general purpose register and another is the special purpose of registers. Sometimes we can say general purpose is the scratch pad registers, and these are programmable and mostly used for data processing and program execution during for any instruction execution. And program counter is loaded with the address of the memory of the first instruction locating of a program. After fetching, it is increased to point to the next instruction. After loading the first instruction, it will increase according to the location of the next instruction. Okay, if your memory is a byte addressable, and suppose you are using some data type which is 2 byte at a time, so it will be increased as a +2. If it is a 1 byte increasable, so it will increase as the 1 byte. And now memory buffer register, that is the MBR. It is completely for the data, our data register MBR. So another is that you will find the MAR, this is the address, and this sometimes MBR also known as the MDR in some books. Memory data register, both are same. All data and instruction pass it in and out of the main storage through MBR. So okay, after getting the MBR, it is found instruction, then instruction will be loaded to the CIR, that is IR also you can say, current instruction register. An instruction to be performed will be taken from the main storage via the MBR and placed in the registers. So this is the one point we would like to mention. And second is that main memory address. It is the prior to each transfer between your MBR and main storage. The exact source or destination of the data of the main storage must be specified by the MBR. Gradually you will understand this point after discussing this. Remember, at this point everything will be loaded in the MBR or MDR, you can say. So memory buffer register is a special register which takes data and instruction, but it also throws storage from your in and out from the main storage, from the main storage to the CPU register, main storage, whatever may be, through that MBR. But MER will specify in exact location of the source where in the main storage the data or instruction is present. So you can say MER will specify the location, and from the location data will be loaded to the MBR. You can say like in this way. Now main memory.
Sir, could you repeat what the CIR does, sir? I didn't get what the
The
CIR.
instruction register. That means if it is found that after MER, when it is specified, it is an instruction, not data. So instruction cannot be processed by the like a register. So instruction to be decoded. What does it mean actually? What to be performed? So instruction register will load the our instruction. Suppose your instruction is add A, B. Suppose these are the registerable, no problem. But when add will be loaded first, what does it mean of the add? Then it will go to the IR, instruction register. Instruction register will be loaded with the instruction and it will decode the instruction. And instruction register decoding signal will go to the control unit, which will generate the particular enable disable for the this or this location where it is required. Because entire task is performed by the CO. CO is the manager of the CPU, you can say. He will do entire management of the instruction. When I am taking the classes, other can't take your classes. You should be available here. Or some people are trying to access other classes, or maybe it is trying to access with their without official mail. It will be barred. So everything will control unit sequences. When A and B will be loaded, other register may not even trying to fetch the data. Control register will disable the path that it will be registered from register data will be loaded from other drive. It will be not loaded. Then how we can understand? Now add instruction, when IR will find, IR will directly decode the instruction using decoder, because decoder size also depend on the instructions architecture. I am not going more details because day by day will go. For time being, you just remember IR will load the current instruction and it will decode the instruction. It's semantic, you can say what is the meaning add. Then accordingly it will generate the required control signals, not control signal, control signals, multiple control signal, micro instruction will be executed to perform as a single task of add also. Because
So,
when add
basically,
instruction will be loaded, it will add for which stump to register, then it will enable to the register, then data will be available to the ALU. Now ALU should be activated, a full header in the ALU, maybe full header, maybe locator, whatever available in the ALU. Arithmetic logic unit perform the task, then it should be enabled, otherwise logic unit will be enabled. So like in this way, for a particular single add instruction, multiple micro instruction will be executed. That will be studied in the we'll study in the control unit general design. For time being, IR decode, take the instruction and decode the meaning of the instruction, and it will be performed by that. So current instruction register always take the current instruction to be executed via MBR. Okay, and
so basically, basically
yes.
MBR, basically MBR has the data and instructions. MAR checks whether it is data or an instruction, and CIR decodes if it's an
Basically, MR
instruction.
specify where data and instruction to be present. It specifies the address of the data as well as instruction. When instruction is loaded to the MAR, MBR, automatically MBR it will go to the directly IR. But when data will be loaded, it will not go IR. It will go to the register. Is it clear? Because data does not require for decoding. It is a raw data. It will be directly used in calculation through registers. But IR, instruction register, it have to decode it, because without decoding the instruction, the sequences operation to be performed by the control unit cannot be done. That's why it separately go to the instruction register where it performs the decoding tasks, and then sequence of micro instruction will be generated by control unit.
So the data goes to the general purpose registers or the program counter registers?
Which one?
So, sir, in case the MAR detects data,
Yes.
where does the data goes to the general purpose register?
Yeah.
Okay, okay, sir. Thank you, sir.
But instruction, then it will go for the IR.
Okay, sir. Thank you,
No
sir.
data will go to the IR. IR specially for instruction purpose. Why? In control unit design, you will find that there is a main purpose. In control unit design, device is called that is IR. And that I will find what is the implementation of the IR because IR record the instruction. Okay. I will discuss a little bit. I will activate the what called whiteboard after these classes, and then I show detail how the execution takes place. Okay. For time being, I have to finish. Okay. Now this is the main memory. I think it's clear to you. To be clear.
Sir, your voice
Sir,
is
your
cracked.
voice is cracking, sir.
Okay. Okay. Maybe network. Now it's clear. Just for
No,
me,
sir.
I
No,
am
sir.
one
Sir.
so maybe you have to audible now clearly.
Unclear, sir.
Am I clear or not clear?
No,
Audio?
sir. Sir, it's
Yes,
still
sir.
glitching,
Clear
sir.
now.
At times.
Okay, okay, a little bit, maybe network issue. I'm trying my level best to make it clear. Nowadays, all the devices of the institutes are
Yes,
available
sir.
to us, so there will be no interruption from our side to your study.
Yes,
I
sir. Now
think
it's clear, sir.
quality is now better.
Yes, sir. It's better now, sir.
Okay, even though I'm checking the device. Is my mic working now?
No, sir.
I'm not audible.
Sir, your voice is very low.
Now is it okay?
No, sir.
No, sir.
Volume is very low, sir.
Yeah, I'm trying. Maybe some else. Subjective computer organization little bit difficulty. Each of every point should be clear. Otherwise, am I audible?
Yes,
Yes,
sir.
sir. Yes, sir. Now you're
Yes,
audible,
sir.
sir.
Yes, sir.
Okay. So it is audible to all of you.
Yes, sir.
Yes, sir.
So finally, the slide is visible to you. Memory.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes.
So now we are in the main memory zone. very close connected to the CPU, contents are quickly and easily changed. Contents are quickly and easily changed. Hold the program and data that process are actively working with. So most of the students are asking when we are doing writing C programming and we are executing C programming, where its presence, see the location, main memory, interacts with the processors millions of times per second. Nothing permanent kept in the main memory. So that's why it's the best example of volatile memory. So I think in the CPU you found such type of slots where we are keeping the main memory. Inside the laptop, it is not stand up. In the laptop, like in this way, we insert it, whatever maybe. So it's look like in this way. It's a laptop memory or it is maybe desktop. So this is the RAM. Look like how does it actually look? Okay. So one is random access memory. That is the RAM part. Another is the ROM. That is non-volatile. ROM is non-volatile and RAM is volatile. Why volatile? You know in the class earlier classes you have studied so far that when the switched off, the circuit has no power, the contents of the RAM will be automatically erased. But in the ROM, which is required for bootstrapping programming, it will be loaded in the ROM for permanently whenever power on or switch on or off does not matter for this one. So software checks the computer's hardware and then load the operating system. So that is the main we call it a bootstrap operation. Generally, that bootstrap operation should be there in case of ROM. So both are in main memory category, but our main purpose that the RAM is the main where we user programs are doing. Here no user program is a built-in programs are there. Here you can do the user programming. Though ROM can be erased and you can again write the content of the route or can be updated the content, but be careful, it's a permanent whatever you do the updated or something else. But in case of random access memory, the instruction that computer is running, every time it is changing, it is continuously changing. So don't take that, sir, sometime ROM is updated, my BIOS is updated, sometime telling that means some instructions are altered or modified, but it's stored in the permanently. That means if there is no power, the content will not be erased in the ROM. So that is the main thing between the RAM and ROM. So in case of RAM, if I pictorially say, you'll find that one is the address of the memory cell and the contents of the memory cell. This is the very important part. We can say these are the address will specify the number of size 2 to the power n-1. If your RAM is 8 GB, suppose 8 GB RAM means 2 to the power 20 GB into 2 to the power 3 for 8. Am I correct? So 2 to the power 23 you will get in cases from that means 2 to the 23 bit classification. So you will get 20 and finally you will get up to here up to 2 to the power 23 location will be there in the RAM. Now imagine what are the number of locations are there. It can access up to 2 to the power 23. Now your memory width is the memory width particularly I mentioned in this W. That means each location contain how much. Here it is mentioned the byte addressable. So 8-bit memory we are considering. That means for particular location I can store 8 bits, and now I have a 2 to the power 23 location, and each of them location I can store 8-bit information. Now address with how many bits used to represent the each address. So here I have mentioned how many address are represent. 23 bits are required. 23 bits address for 8 GB memory. If you have a 4 GB, then automatically it will be reduced. Am I correct or wrong? So like in this way, when 22 bits are required, so this is the address width. If address width is n bit, then address space is total 2 to the power n, that I have mentioned now, just like in this way. Is it clear this point? Now RAM static and most use the contents of DRAM. The contents are repressed with the presence of some capacitor. In the memory architecture, we will go more details for timing. You know,
Sir, you are again cracking,
yes.
sir.
What?
Sir, you're again cracking, sir. Your voice is again cracking, sir.
Getting me?
Sir, your voice is again cracking, sir.
This is the network issue. Don't worry. Slide will be visible to system, so you will get it very soon. Okay. So static RAM. Now it is visible to you.
No, sir.
So first of all, we are audible.
No, sir. It's still
No, sir.
cracking.
Again, audible. My God. I don't know what happening every time. Suddenly network falls.
Now it's good, sir.
Is okay.
Yes, sir.
Is the sound okay or not?
Now
Yes,
it's
sir.
okay,
Now
sir.
it's okay, sir.
Yes, sir.
With network fluctuation. Okay, after that you will find that I am doing some concept static RAM. Each cell store bit with six transistor circuit. So here you will find 1, 2, 3, 4, 5, 6. 6 transistors are there. Retains value indefinitely as long as kept power, is like a RAM concept. Faster, more expensive. So if I make SRAM based concept in everywhere, the cost of the product will be very high, that it is beyond the capacity of the normal person. So that's why mostly we are go for the DRAM. Each cell stores bit with a capacitor and transistor. Value must be refreshed every 10 to 100 milliseconds because the charging of the capacitors, and slower and cheaper than SRAM, has reduced power consumption and large storage capacity. Advantage that maybe speed is slower than this one, speed is lower, but mostly it is storage capacity is high. Storage capacity is high. So if we would like to go for economical option, I can go this for cache memory design and this for main memory design. This cache is faster than memory. We know we have to make it to reduce the bandwidth, but to minimize the cost also, we will go for this one. So that is the application of DRAM, slower but cheaper, and as well as the power consumption also very less, and large storage capacity we can make using DRAM. That's why drastically the cache size we can't so much increase. The cost of the cache is so high, so I can't make as a GB at this moment. Now it is in KB. And little bit L1, L2 MB, but the 8 GB main memory is possible by the application of DRAM only. And non-volatile RAM, that is NVRAM, retains all information and power is turned off. Use particularly virtual desktop server computers, since I use DRAMs from the main memory and SRAM for cache. So this is the point I would like to mention here. After that operations of memory, now it is coming two operation from the memory. From if it is a memory and is the registers are there, maybe whatever, for main memory I have to fetch, and after computation I have to store. This is the two fundamental instruction, fetch and store. And here is the two step execution. If instruction, there is a ID. So I am finding basic fundamental step. First fetch the instruction. After fetching, you decode the instruction if it is instruction, then you execute the data, execute, and then you store the data. This storage and fetching, it is from main memory and it is to memory. I am not telling main memory is memory. So fetching and storing, that's why I have written fetching means here, fetch means the fetch a copy of the storage. That is a very important point here. Fetch the copy content of the memory cell with the purpose of this one. So actually you are fetching a copy of the contents memory cell with this part, and it is a non-destructive fetch operation. A fetch operation is non-destructive. Remember this point. Fetch operation is non-destructive. Means copies value in the memory cell. The content of the memory cell not altered. You just read the value, bus. That's the sufficient. You are just reading the value, but the contents of the register not, or memory location not altered. That's why it is called non-destructive. But store the specified value into the memory cell specified. It may happen that you are storing the same value again, but it will be override. That's why it will be destructive operation. The previous value, if it is same, it will override. If it is new value, it will ever update with the new contents. These two operations are recorded in the memory. and this instruction execute and it takes place within the CPU. That's why I'm not dealing with the memory part. Now, structure of the memory. If we find that whenever CPU try to access any data or any instruction, what happened that first fetch instruction is trying fetching, because store program concept, everything there is the main memory, you have to fetch it first. Now load address to the MAR. That's why I'm telling that MAR is first loaded. Clear? Now if CPU asking a value, then it will directly load it in the MBR. Here will be MDR. If CPU asks some instruction, that will be loaded to the MAR. So whatever may be, data and instruction somewhere present in the main memory. Data instruction somewhere will be present in the main memory. So it is our memory, somewhere location I have to specify. I have to note the location. That's why the memory decoder circuit will decode the part. How does it look, memory decoder part? You now see whatever memory data content will be loaded to the, it is how many bit? 4 bit, suppose 4 bit line. So 4 bit can decode in decoder circuit. What is the size? 2 to the power 4. That means 16 lines will be there. Am I correct or wrong? You check here 00 to 15. So 16 possible locations are there. So based on the decoder, based on the memory, decoder circuit will increase. So it may happen that the decoder circuit may be, here I have starting 0, here 15. So I can say location 15 locations are only there. 16 locations are there total. 16 locations are there. Make it silent. Okay. 16 locations are there. Now you know these 4 values are there. So these 4 values from where come? Decoder. So go to the decoder. You will find that from the memory address register, the value will come to the decoder circuit, and decoder circuit will decode at which locations present. As I mentioned, the locations are anywhere of the locations present. Now from here the data will comes out, and the data will be loaded now to the our fetch controller. It will be loaded to the memory data register. So data will be loaded now, memory data register. Am I clear at this point? Clear this point to all of you? Data will be loaded now, memory data register. If it is found instruction, then it will go to the IR. Otherwise, it will go to the directly register. Am I clear? So this is the our memory subsystem. Two special are used. It can be register bank, it can be memory. That's why I'm telling is a memory. So in the during the storing, again it will be loaded to the memory. Again it will be decoded the location, and from the memory data, from the memory, that is the fetch and store for controller. For storing, it will be go like in this way. That's why I have given both side arrow. Be careful during giving the arrow in the examination. Students always do some mistakes during the examination. I am telling you, just remember this point. See the condition of the arrow, very important point part. That instruction from where it is coming. Whether you are doing some fetch or you are using some instruction, this instruction actually coming from your control unit. After decoding the meaning, it will come that instruction, that it will be fetch operation or store. If it is store, it will go from memory buffer to the this location. If it is fetch, it will come this location. Am I clear at this point? So like in this way, copy the contents of the MDR into memory cell with the specified address, it will be loaded. Now like in this same thing, about after decoding, the instruction will be stored, and when it is found after decoding and it is a fetch instruction, it will be stored at the specified location. Now this memory has some problem. Every time it will be 0.
Sir, one
every time I
request,
have to
sir.
start from the location. We are using two Endian format. It's called two Endian. One is big Endian, one is the little Endian. In little Endian, the LSB part is loaded first in the our lowest part in the middle. So little Endian and big Endian. That means Sun microsystem max area big Endian. Max system they are using big Endian. That means least significant bit has the highest address. So you will find, suppose our address is that 4 byte presentation, this is our address. So I am continuing 2 byte address I am considering. So what happened that in big Endian format, you see the MSB is loaded in the lowest area and LSB is loaded in the highest zone. So this reverse happening. In the little Endian format, lowest come in the lowest and highest come to the highest location. So big Endian is the default thing. Now, which is better? It is a Gulliver travel story. Nothing. Gulliver also good and Lilliput also good. Who has survived the same purpose? So, Indian does not matter which is strong or big. It depends on the architecture you are managing just. But I am telling that is the byte how order. That means in the main memory I have told the content of the word maybe say 8 by 8 bit. So it may happen there is a 4 locations are there or maybe 8 locations are there. In big Indian format, the most significant bit will come in the first location. In little Indian format, little Indian lowest bit come first and MSB go as the last. So this is the two type of formatting of the writing only, nothing else, all are same. Okay, so PCs, that means Intel, our microsystem, Intel processors or whatever we are using, mostly we are using little Indian, but Macs are using the big Indian format to store the data in the memory. So that is the Indian format. Now go to the CPU basics. So we discussed the memory part, the first part that is called main memory module. It is clear. Details main memory, that means how data is coming, how data we are storing, where to store, what is the technology, how mapping will be done, can be overlapped in the same location not. So it will discuss in the main memory chapter and the memory management system. But for first class introduction, the principles of the memory, how data is stored, what type of the technologies are exist in the memory, that we have discussed so far. Now we are going for the CPU part. Today I think after 3 hour class, just 10 minutes give me more, then I will finish these slides. Okay, from your side? Is it possible to continue?
So 3
3
o'clock plus
o'clock we have
class.
another class.
Yes,
So 3 o'clock we have another class, sir.
at 3 p.m. now.
Yes, sir.
Just 10 minutes more, because otherwise you will lost the sequences of the classes, that means topics. 10 minutes I am discussing, okay?
Okay, sir.
Just 10 minutes, no more. Now the CPU basics, the computer CPU fetches. Now this is the instruction: fetch, decode, execute, and final step is store. So these are the 4 phase, you can say. Some computers the multi-phase also there. The number of phases instruction maybe that means phases will be more. Here basically we are considering 4, but it may be more than 4 also possible. Two principal parts of the CPU is there. One is data path, one is the control unit path. In data path fully we are considering the all the connections with the banks. This is our register banks. So data dealing with the register banks, special purpose register also there registers. So these are dealing consist of arithmetic ALU, storage unit register, interconnected by a data bus that is also connected to the main memory, that is connected to the main memory also. So this is entirely data path. Whenever we will say in the data part with, always deal with the interconnection required to transfer from the main memory to register, register to main memory, and register banks as well as the as well as your ALU. This entire unit contains the data path. Now in control unit, there is a special purpose control unit who actually control which register line will be activated, from where which line will be activated, which operation will perform now, everything, the entire sequences. So responsible for sequencing the operation and ensuring the correct data stay at the right location, the right time. Be careful this point, right data at right location. That is a very important point. Most of the time we are skipping. So right data at right location. That is the task of the control unit. Now, if I go for the ALU which part? It is the part of the data path. Remember that discussion. It is called the data path. This is our CPU's main component, where I am giving you the all the registers are connected. You must, after getting the slide, you must practice all the figures, because anytime any figure will come in the examination and you have to draw it. But especially you consider the sign of the arrow. If you misplace the arrow or missing the arrow, I will understand that architecture not clear to you. The very important point. Whenever write data bus to the IR, it means that instruction from data bus to IR for storing and for fetching also you need both the connection. And database is a multiple connection. You see multiple, because sometimes data will be loaded, then fetch and for store, but it is only one dimensional. Why? It always go for the instruction to be searched, where it will go. So address bars always go to the current address. Address cannot be fetched here. Address only for location finding. Am I correct or wrong? So be careful all the signs I am using. See, all the data in register connections are bidirectional, means that it can be loaded to the register, it can be fetched to the, it can be stored to the also, it can store, it can fetch. Is it clear this point? See, in ALU part there is the accumulator. This is the accumulator part. Accumulator is feedback to the register feedback. Then you can say every time accumulator will be there. Then if I would like to change the data of the that means one data will come here, other data will come from where? You use some multiplexer here. That I'll show more details here. By the application of multiplexer, if there is a multiplexer, so if it is store or if it is load or store instruction, suppose, so is a multiplexer MUX, some from register, some from accumulator. If it is store signal, then accumulated data will come and store here. Accumulated data will be come here, and from here register it will go to the main memory. But if it is a load, then accumulator will not be activated. This line will be activated. It will be come from the memory or from register to new data. So by the application of the multiplexer, we can control here. I will discuss little bit more when go for the internal structure for this one. For time being, you just ignore it. Is it clear? For time being, it is not required to think about the more details of this part. Now, our main consideration is that in the ALU part, if you recall that ALU part, you will find that registers are main very important component for the registers. Then you will find another component is called our ALU circuitry required for transaction and the bus connection to the data set. So this the internal structure, more details I have given here. In control unit, signals are coming from somewhere. I will discuss these figures, so you will get more on this type. From the next class, I will go for the control unit and then this chapter will finish.